Imagine you're sitting down to eat a salad over lunch. Now your salad doesn't have any dressing on it, so you reach over and grab a bottle of hydrochloric acid to add to your salad as a nice light dressing. Now you might be thinking, now wait a minute, hydrochloric acid, that's a strong acid. I don't want to be pouring that on my salad. And that's true. Hydrochloric acid, it's very strong acid, it would burn your throat, it would burn your mouth, it would cause serious damage if you put that hydrochloric acid on your food. And yet, we think nothing of pouring acetic acid, which we commonly call vinegar, onto our salad in the form of balsamic vinegar, or of course many different salad dressings that contain that acetic acid. So if we compare our hydrochloric acid, or HCl, and acetic acid, the question then is, what makes these molecules so different that one is a strong acid that will burn our mouth and throat, and the other is still an acid, it's still acidic, but it's not a strong enough acid to be dangerous to us. And in fact, it can be enjoyed in a lot of different food products. So again, we have our very strong acid, our hydrochloric acid here, and our weak acid of acetic acid or vinegar. Now, of course, the first thing that we need to think about here, in order to understand why our hydrochloric acid is a strong acid and our acetic acid is a weak acid, we first need to understand our definition of acids and bases. So our standard definition of acids and bases is our Bronsted-Lowry definition. So a Bronsted-Lowry acid is something that donates hydrogen plus ions. All right, so we donate H plus as an acid, so our hydrochloric acid and our acetic acid are both giving away H plus. And then we're always reacting in an acid-base reaction with a base that would then be accepting that H plus that we donate from our acid. So we're going to take that H plus, give it from our acid to our base. Right? So we typically write this out. So we might have our hydrochloric acid reacting with water. So water will act as our base in this scenario. And we react to produce our hydronium ion. And our chloride anion as the conjugate base of our hydrochloric acid. So this is our basic acid-base reaction. Now, of course, we've seen how we can use curved arrows to show the electron movement that's occurring as we make this reaction. So our hydrogen, we take our electrons from our water, and we show the movement of those electrons that are coming over and making our new bond here with our hydrogen. That results in our hydronium ion here. And then, of course, at the same time, we take the electrons from our hydrogen-chlorine bond, and we break that bond and move our electrons onto our chlorine. Now again, these arrows show where our electrons are moving, and there's a reason why we want to show this electron movement. And that is because it helps us to understand the reactivity of our system. So previously we talked about how we have different areas of high electron density or low electron density. Right? So our oxygens here are pulling electron density away from those hydrogens. So we get this partial negative charge from our oxygen pulling on those electrons and pulling it towards itself. And that means that we have lots of electrons here that we can use to attack our hydrogen over here and make that new bond. On the other hand, over here, our electrons are getting pulled away from that hydrogen towards our chlorine. So our chlorine gets a partial negative charge, and our hydrogen gets a partial positive charge. So we have this little positive charge here that's attracting those electrons that are coming over to make our new bond. So again, the key thing to remember is that electron distribution is usually what will determine our reactivity. And this is the case for most reactions that we'll look at in organic chemistry. It's all going to be about looking at where we have areas of high electron density, like our oxygen here. Again, we'd also call this a nucleophilic site, an area of high electron density. And we have our areas of low electron density that we call our electrophiles or our electrophilic sites. So these, again, will be determining our reactivity, but of course there'll be other factors that will make this more complicated as well as we look at our different reactions. So we're going to look in detail at our acid-base reaction here and look at the different factors that affect our reactivity so that we can start to gain an understanding of how we can determine the reactivity of our compounds. The first factor that we'll look at that affects the reactivity of our acids is electronegativity. So of course, as we've already seen, electronegativity changes the distribution of electrons in our molecules. And this will have a huge effect in our reaction right here. So when we're looking at electronegativity here, we're focusing on the electronegativity of our chlorine. So the electronegativity of our acid, specifically the atom that's bonded to our hydrogen that we're donating when we react as an acid. So as we just said, of course, our hydrochloric acid here, we have this unequal distribution of electrons where our electrons are focused on our chlorine, right? Our chlorine is pulling those electrons over towards itself, and our hydrogen becomes electron deficient. Now, since we're trying to donate that hydrogen as an H+ ion, the more our electrons are pulled over towards the chlorine, the easier it becomes to pop that hydrogen off to make our H+, right? Essentially, the bigger this difference is in electronegativity, the closer our hydrogen already is to becoming that H+. Right? If you imagine a scenario where our chlorine is super strongly electronegative, it's way stronger than our hydrogen, then it just takes those electrons away from our hydrogen, and then it becomes a chloride ion, and we have our H+ ion. Of course, we're very familiar with this sort of scenario because this is exactly what happens when we have sodium and chlorine. Right? So between sodium and chlorine, we have our two electrons, and of course, instead of forming a covalent bond between our sodium and our chlorine, our sodium has such a strong pull on that electron that we just donate that electron over to our chlorine, and we make our chloride anion and our sodium cation. So this becomes an ionic bond because the difference in electronegativity is so large. So the same kind of scenario happens here with our hydrogen and our chlorine, where the stronger that difference in electronegativity is, the closer a hydrogen comes to becoming that positively charged cation, and therefore the stronger acid we are, right? The more easily we can produce that H+ and then donate that to our base. So more electronegative, atoms are more acidic. And of course, they also have to have that hydrogen attached in order to, of course, be able to donate a hydrogen plus ion. If you don't have hydrogen, you can't donate a hydrogen, obviously. So if we compare hydrochloric acid with, say, methane, so methane, we just have hydrogens attached to carbons. Carbon is further to the left on the periodic table, so it's less electronegative. And because of that, our carbon here actually is not at all acidic. So carbon has relatively low electronegativity compared to things like nitrogen, oxygen, chlorine, and fluorine. And so between our carbon and hydrogens, we have very low acidity. Our second key factor that will determine our acidity is the strength of our bond between our hydrogen and our acidic atom, our tyrosine A. So again, of course, if we look at our mechanism up here, shown with our arrows, in order to make our products here, we have to have our electrons come in and make a new bond, but then we also have to have our electrons break this bond and move over to our chloride. Whenever we break a bond, that requires a lot of energy, right? Breaking bonds, we have to spend energy. Forming bonds actually gives us energy, right? So it costs energy to break that bond, and so if our bond is weaker, it'll be easier to break that bond, and then it'll be more likely for our acid to react, break off our hydrogen, which we can then donate and form, of course, our conjugate base. So a weaker bond between our hydrogen and our acid will create a more acidic acid. More acidic compound. Now, of course, you might be wondering, what makes a weak bond, right? How do we know if a bond is going to be strong or if it's going to be weak? One of the key factors that affects bond strength is the size of our atom. Right? So imagine we have our hydrogen chloride. So here's our hydrogen, here's our chloride, and of course they're bonded together with our covalent bond. Now, the smaller our atoms are, or the more similar they are in size, the stronger this bond is going to be. Right? So if we compare our hydrochloric acid with hydroiodic acid, so our iodine is lower down on the periodic table. That means it has a lot more electrons, and so it has this very large atomic radius. Right? So we have a very large atom down here. Since we are lower on the periodic table. So now we have the small hydrogen trying to interact and form a bond with this very large atom. So the size mismatch makes our bond weaker. We also, of course, are going to be much farther away from the nucleus of our iodine. Right? So our nucleus is way down here at the middle of our atom. And we have quite a large distance between our electrons out here and our nucleus with its positive charge way out here in the middle. So that large distance means that there's less attraction between our negative charged electrons and a positively charged nucleus. And of course, our bond is really mostly based on that attraction between our nuclei and those electrons, right? It's both of our atoms, their nuclei, getting attracted towards those electrons and then sharing those electrons between our two atoms. So as we get our larger atoms, that leads to weaker bonds, which then leads to increased acidity. So based on this factor here, we can say that HCl, our hydrochloric acid, is actually less acidic than hydroiodic acid. Right? When we have that larger atom size, that makes this a much stronger acid. This can also start to answer the question of why our hydrochloric acid is a stronger acid compared to our acetic acid. If we again look at our acetic acid, so here's our acetic acid here. So our hydrogen that gets donated is this hydrogen right here at the end. It's attached to an oxygen, so that oxygen of course is electronegative, which makes it somewhat more acidic, especially compared to like these carbons over here on the left. But our oxygen is at the top of the periodic table. It's a relatively small atom, whereas our chlorine is down another row on the periodic table. So it has a much larger radius, and so that results then in a weaker bond, and it makes our hydrochloric acid much stronger compared to our acetic acid. Our third key factor that affects acid reactivity is what we call the inductive effect. Now, as we've discussed, our electronegativity has a key influence on our reactivity because it creates this difference in electron distribution and this difference in charge in our molecule. Right? So our electrons are already pulled more towards our chlorine. That makes it easier for us to break our bond to our hydrogen and then of course donate that as our H+ ion. Now, it turns out electronegativity can affect our acidity even if we're not just looking at that atom that's directly attached to our hydrogen. So let's look at a scenario here. Let's compare our acetic acid so here we have our acetic acid again. And we can compare this against some other slightly different acids. So here we have an acid here, which looks very similar to acetic acid, but we're going to add a fluorine over here on the left-hand side instead of our one of our hydrogens. So again, we can look at the similarities in our structures. We're looking at the acidity of this hydrogen here at the end. And of course, we can say, if we look at our first two factors, our oxygen is bound to that hydrogen in both cases. Same electronegativity, so we'd expect the same acidity based on our first factor. Our second factor, we look at the bond strength. Well, of course, both cases, it's an oxygen-hydrogen bond. So the bond strength is the same in both cases. Now, if we look at this inductive effect, so our inductive effect looks at how other electronegative groups affect this bond over here. Now, how would our fluorine here affect our hydrogen? So fluorine, of course, is in the top right side of our periodic table, which means that it's highly electronegative, and it's going to be pulling electron density away from our carbon to create this partial negative fluorine and a partial positive carbon. But for our molecule, we really can't think of it as just being individual bonds between different atoms. Our molecule actually kind of shares electron density all throughout the molecule, right? Our whole molecule really is bound together. It's not just individual atoms bound together. So when we're pulling electron density here, it actually affects the rest of our molecule as well, right? So we can really think of this as a cloud of electrons kind of all around our molecule, and we've got this selfish fluorine over here that's basically pulling that cloud of electrons more over here towards our fluorine, right? So that pull from our fluorine actually pulls some electrons from our carbon over here, and our oxygens, and our hydrogen as well. So even though that fluorine isn't directly connected to our hydrogen, it's still going to be pulling some of that electron density towards itself, and it's going to end up pulling more electron density away from our hydrogen. Right? So it's doing the same thing that our oxygen is doing, as it's directly pulling on that hydrogen, but it's just a slightly weaker effect because it's a little bit farther away. So this effect is very distance dependent. Again, if we made a very similar compound, but we moved that fluorine a little bit farther away, this would be slightly less acidic. So here we still have our fluorine, and it's going to be pulling electrons toward itself based on its electronegativity, and that's going to be shifting electrons from the rest of our molecule over towards that fluorine, again making our hydrogen slightly more positive. But since it's farther away, we feel the effect of that pulling fluorine less than we do for our molecule here in the middle. So if we compare our three molecules overall, our acetic acid with the extra fluorine, or our acetic acid with the carbon and the fluorine, to put our fluorine further away from our hydrogen over here, this is going to be the most acidic because it has the strongest effect of our fluorine pulling electron density away from that hydrogen and making it more positively charged. This is going to be the least acidic because it doesn't have that extra electronegative fluorine pulling electron density away from our hydrogen. And this will be our middle acidity, our intermediate acidic compound. Since we have that fluorine that's pulling electron density away, but it's a little bit farther away from our hydrogen than it is in the central case, and so it has a weaker effect. So our inductive effect can be summed up as electronegative groups particularly groups that are close to the acidic hydrogen pull electrons away and increase acidity. So it's affected both by distance, and of course it would also be affected by the number of electronegative groups. So if I replace another hydrogen with a fluorine, I would make this even more acidic. We'd be pulling more electron density away, increasing the partial positive charge of that hydrogen and increasing our acidity. The final factor that determines how strong our acid is resonance stabilization. In order to look at this factor, we're going to take a closer look at the reaction of our acetic acid. So of course when acetic acid reacts as an acid, our reaction is going to look very similar to when hydrochloric acid reacts as an acid. So again, we're going to take our electrons from our base, our water in this case. We're going to use those electrons to make a bond with our hydrogen. Again, my arrow is showing that pair of electrons going over and making that new bond to make my hydronium ion. And we're going to take those electrons from our bond here. We break that bond, those electrons go and move over onto our oxygen. One of our oxygens ends up with a positive charge. One of our oxygens ends up with a negative charge. Now, in order to understand this resonance stabilization factor, we have to realize that most of our reactions are actually equilibrium reactions or reversible reactions where we can react and form these products, but then these products can actually react backwards to form our reactants. Right? So this, of course, is our conjugate base of our acetic acid. And this is our conjugate acid of water. So we have an acid and a base on the right-hand side, and an acid and base, of course, can react together in an acid-base reaction. All right, so we have this oxygen with 3 lone pairs. It has a formal negative charge, which means it has a high electron density. We have this oxygen over here that's pulling electrons away from my hydrogens to make my electron deficient hydrogens. And so I can take my electrons, come over here, make a bond to that hydrogen, and then break my bond here to move my electrons back onto that oxygen. All right, so this reaction can react to produce my reactants over here, combining my conjugate base and my conjugate acid. So in order to understand the acidity of a compound, we really have to answer the question of, would we prefer to react and make these, or would we prefer for these to react and make these over here on the left, right? If something is going to be a strong acid, that means that it's going to react and we're mostly going to have our products. A weak acid is going to have more of a mixture of our reactants and our products. So something that creates a really reactive conjugate base tends to be a weak acid, because that conjugate base would then react with our conjugate acid and would actually end up recreating our weak acid. Now, when something tends to be very reactive, we refer to it as something that's unstable, right? It doesn't stay in its current state, it wants to react and make something new. So if we can stabilize something, create something that's more stable, that's going to be less likely to react, right? So anything that's more stabilized is less likely to react, anything that's less stabilized is more likely to react. So if we have stabilization of our conjugate base, then it will be less likely to react backwards to remake our acid. So we're specifically looking at resonance stabilization of our conjugate base. So we want to stabilize this conjugate base here so that it's less likely to react and reduce the acidity of our weak acid. Now, what do we mean by this resonance stabilization? How can we stabilize something in order to make it less reactive? Well, of course, as we've said, one of the things that makes something reactive is when we have a large distribution of electrons in our compound, right? If we have an area of high electron density, those electrons are likely to want to move and make a new bond, like we see here between our nucleophilic oxygen and, of course, that more electrophilic hydrogen, right? We have the negatively charged electrons moving over towards that partial positive charge so that we can make that new bond. So in general, we want to reduce electron distribution differences so we want to reduce the differences in electron density or in other words, we want to spread our electrons out throughout our molecules. There's no one place where we have a lot of electrons we're going to be more reactive. So one of the ways that we can do this is with resonance. So let's take a closer look at our conjugate base. So this is how we've drawn out our conjugate base. But again, it's important to realize that our electrons don't really belong to any specific atom in our molecule. They can actually move around and be shared in our molecule. So we can actually take our electrons and we can move them between different atoms or different bonds in our molecule in what we call resonance, right? So these aren't different molecules, they're just going to be ways of rearranging our electrons within the same molecule. So we can't just take any bond and move it, right? So if I take this bond and move it over onto my carbon, so that'd be showing these two electrons moving over, and we get to my two electrons showing up on my carbon. Like this. So I would end up with a negative formal charge here since it gained an extra lone pair, and a positive formal charge here since it lost that bond. So this would not be possible because that would be breaking apart our molecule, right? So resonance is not looking at a reaction or a breaking molecule, it's just looking at how we can kind of move our electrons around within our molecule without breaking it up. So that's the first rule that we need to think about when we're moving electrons around our molecule with resonance. We don't want to break the molecule. Now, the second possibility, we can start to move our electrons. So I could take some of my electrons here for my oxygen, and I can move them in here. So I'm taking this lone pair, and I'm using it to make a new bond, a double bond, since I already have one bond there, between my carbon and my oxygen. So let's draw the resulting molecule over here. So I move my electrons in. Now, of course, if we look at our carbon here, so it has 5 bonds to it. Each of those bonds would have 2 electrons. So that means we have 10 electrons around our carbon. Now, 10 electrons, that exceeds our octet, right? We have more carbons around our carbon than it needs to fill up its outer electron shell, which never actually happens. Our carbon doesn't want to gain those extra electrons because it doesn't want to go beyond that full shell. So don't exceed the octet. So we can't just move our electrons in there because that would exceed our octet, and then we would break, and our carbon wouldn't be happy in that state. But if we move our electrons in here, and at the same time move these electrons up onto our oxygen, now we create a new resonance structure. So this is still the same molecule. We still have the same bonds, the same atoms bonded together. But now we've actually moved our electrons from one oxygen over to the other oxygen, and we've moved our negative charge from that lower oxygen up to our upper oxygen. So by moving that charge around, what we've done is we've effectively spread out or reduced the difference in electron density. Right? So our electrons can actually move freely within our molecule. Right? So these are our two different resonance structures, which neither of these structures actually exist. Our molecule is actually just moving those electrons back and forth to create a resonance hybrid, we call it. Where our electrons are actually spread out between our two oxygens. So I have my two oxygens. I'm using these dotted lines to represent a partial double bond, and our lone pair and our negative charge is actually shared out and distributed between those two oxygens. Right? So neither of them have the full negative charge. They each kind of have half of the negative charge as it's shared out between those two oxygens. Now, of course, what we've done here, again, is we've created two oxygens that each have lower electron density compared to our original oxygen here. When we reduce that electron density, we make it less likely that our oxygen is going to attack a hydrogen and break it off to reform our original weak acid. And so therefore we make our conjugate base less reactive, which then means that our original weak acid is actually a stronger acid. Right? Because it's more likely then that it will react, and we'll get to this conjugate base. This conjugate base will be happy the way it is because it's able to spread out those electrons where we don't have any area with lots of electrons that's likely to react. So it's less likely to react, and therefore it's more likely to just stay in this state, and so we react and just end up with our conjugate base forming, and less of that conjugate base reacting backwards to reform our weak acid. So these four different factors are key for determining how reactive our acids will be. Again, as we move up in electronegativity, so moving to the right and to the top of our periodic table, we increase the electronegativity, which increases the partial positive charge on our hydrogen and makes it easier to lose that hydrogen. As we move down the periodic table, our atom size increases, which makes this bond weaker and easier to break as we're looking to donate that hydrogen. We can also, of course, pull electron density away with other electronegative groups attached to our acid, or of course, we can stabilize our conjugate base so that after our acid reacts, we're less likely to just react backwards and reform our acid. So going back to our original question, again, of hydrochloric acid versus acetic acid, the primary difference there is just based on factor 2. Our hydrochloric acid has that weaker bond between hydrogen and chlorine, which then makes it easy for that chlorine to break off our H+ and form our chloride ion conjugate base.